When you're building a computer network, what's the one thing you really want? Reliability. So you add extra backup links just in case something fails. It's a fantastic idea, right? Total common sense. But here's the crazy part. That very solution, that smart backup plan, can create a total meltdown that brings your entire network grinding to a halt. So let's dive into this hidden danger and the ingenious protocol that was designed to save us from our own good intentions.
So here's our game plan. First, we're going to walk right into what I call the redundancy trap. Then, we'll introduce the hero of our story, the original spanning tree protocol. We'll see how it elects a leader for the network, how it gives every port a specific job to do, and finally, we'll watch it evolve into the super fast version we rely on today, Rapid PVST+.
All right, let's kick things off with Section 1, the redundancy trap. This is where we get to see how a perfectly logical, well-intentioned idea, building a network that can handle a failure, can just go spectacularly wrong.
I mean, this is the core principle of building a resilient network. If a cable gets unplugged or a piece of hardware dies, you gotta have a backup path ready to go. You never want a single point of failure. It just makes sense. But here's the twist. What if that backup plan actually creates an even bigger problem? Well, down at layer 2 of your network, we're talking the switching layer, it absolutely does. See, without some kind of control system in place, having multiple paths between your switches creates a closed loop. And that loop, well, it's a ticking time bomb. Once that loop is active, it unleashes 3 network-killing disasters. First, you get a broadcast storm. A single broadcast message gets trapped in that loop, circling faster and faster, duplicating itself, and eating up all your bandwidth until the network just suffocates. Then you've got MAC database instability. Your switches get so confused about where computers are that their internal address books become completely useless. And finally, multiple frame transmission, where your poor computer gets the same piece of data again and again and again. It is pure, unadulterated chaos.
And that brings us to Section 2 and our hero, STP, the Spanning Tree Protocol. This is the brilliant solution that lets us have all those extra physical cables for safety while preventing the logical loops that cause all that chaos.
The best way to think of STP is as a really smart traffic cop for your network. First, it looks at the whole city, all the switches and all the connections, and draws a complete map of every possible route. Then, to stop a massive traffic jam, or in our case, a loop, it strategically blocks off a few roads. It puts up a do not enter sign on just enough paths to keep everything flowing smoothly, but it keeps those blocked paths in reserve, just in case there's an emergency.
So, how do all these switches coordinate? Well, they're constantly talking to each other. Every 2 seconds, they send out these little messages called BPDUs. You can think of it as the heartbeat of the network. It's each switch saying, hey, I'm still here, and here's what the network looks like from my perspective. These messages are absolutely crucial. They contain all the info the switches need to work together and build that loop-free map. Which leads us straight into Section 3, the root bridge election. You see, before you can build a logical loop-free map, everyone needs to agree on a single point of reference, a "you are here" star on the map. To do that, the switches have to elect a leader.
And this election is actually pretty simple. First, all the switches throw their hats in the ring by sending out those BPDUs we just talked about. The main rule for winning is simple. The switch with the lowest bridge priority number wins, period. And if there's a tie, no problem. The switch with the lowest unique MAC address wins the tiebreaker. It's a guaranteed way to get a single winner.
Now that tiebreaker is way more important than you might think. Why? Because right out of the box, every Cisco switch has the exact same default priority value, 32,768. This means that if you just plug a bunch of new switches together, the election is basically a lottery based on which switch just happens to have the lowest MAC address. But it also gives network admins a ton of power. They can just go into a powerful core switch and manually set its priority to a lower number to guarantee it becomes the leader, the root bridge.
Okay, so the votes are in. The leader, our root bridge, has been elected. So now what? Well, let's jump into Section 4, because now every single port on every other switch gets assigned a very specific job. This is the nuts and bolts of how STP actually stops the loops from forming. First up, every switch that isn't the leader picks one, and only one, of its ports to be the root port. You can think of this as its personal express lane, the fastest, most direct highway back to the root bridge. This port is always open for business, always forwarding traffic. Next, we have designated ports. Now, for any single cable that connects two switches,
Only one end of that cable can be the boss, the one in charge of sending traffic down that link. That port is the designated port. It's the official on-ramp for that piece of the network.
And finally, we get to the port that actually saves the day, the non-designated or alternate port. If a port isn't a root port and it isn't a designated port, it gets put into a blocking state. It doesn't send or receive any user data. It just sits there, listening quietly. This is our backup link, our redundant path, waiting on standby. And that is the absolute genius of STP. We get the safety of having that extra cable without the chaos of the loop it could create.
But the original spanning tree protocol had one massive, glaring flaw. It was slow, like painfully slow. If a primary link failed and that backup port had to take over, it had to go through this whole 50-second process of listening and learning before it could finally start forwarding traffic. 50 seconds. In today's world, 50 seconds of network downtime isn't just an inconvenience, it's an eternity.
Which brings us, finally, to our last section, Getting Faster with Rapid PVST+. This is the modern evolution of spanning tree, and it was designed from the ground up to solve that massive speed problem.
And honestly, the difference is night and day. It's not just a small improvement, it's a total revolution. Classic STP took a leisurely 30 to 50 seconds to fix the network. Rapid PVST Plus does the exact same job in under 10 seconds, and often it's closer to 1 second. For network reliability, that is an absolute game changer.
You can really see the whole story of this evolution right here. The original was slow but didn't ask for much from the hardware. Then Cisco came along with PVST Plus, which was cool because you could run a separate spanning tree instance for each of your virtual networks, but it was still slow. The real breakthrough came with the Rapid standards. And you can see the trade-off, right? To get that incredible speed and flexibility, the switch has to work a bit harder. But for any modern network, that's a price you are more than willing to pay.
So how on earth did it get so fast? Well, it's all about being proactive instead of reactive. Instead of slowly trying to figure things out after a link fails, Rapid PVST Plus has already pre-calculated the backup paths. It gets rid of those slow old states and just has one called discarding. It officially defines alternate ports that are ready to take over in an instant. All those clunky old add-on features were just baked right into the protocol itself, making the whole system way smarter and way faster.
And this really is the bottom line, isn't it? The entire point of this decades-long evolution was to get the network to heal itself fast. Being able to respond to a major failure in less than 10 seconds isn't just a nice feature. It's the fundamental promise that keeps our modern, always-on networks actually online.
So I'll just leave you with this final thought. In a world that demands instant access and constant connectivity, the jump from a 50-second recovery to a sub-10-second one isn't just a minor upgrade, it's an absolute necessity. It's the silent guardian that lets us build the reliable, redundant networks we need without accidentally unleashing total chaos.